All right, guys, welcome back. And so I wanted to go back and to redo another video that kind of backs us into the previous bit, the beginning part of Organic Chemistry 1. So again, I'm trying to build up all of the content for the entire class so that you guys have access to video lectures that kind of go through everything that we've already gone through up to this point. At the end of the semester, I want you guys to be able to take a look at these videos and look over any particular content that you want to, and kind of get another lecture for that. And so what we've already talked about is we've already talked about geometries and Lewis structures and kind of tied those things together. And then we took an aside over to condensed structures and line bond structures and tied those and kind of figured out why we would want to do that, based on the fact that drawing Lewis structures is tedious, especially for larger molecules. But now we want to take a jump back and talk about three things: valence bond theory, molecular orbital theory, and we also want to talk about intermolecular forces. Intermolecular forces are important because they help you understand physical properties of molecules. And when you think about different functional groups, those physical properties, especially boiling point, come in a big way. So the other things are valence bond theory and molecular orbital theory. You're going to get some folks that are going to say, hey, look, valence bond theory is super duper important. It's the best thing out there. Some other people are going to say molecular orbital theory is super duper important. It's the best thing out there. You know, the bottom line is they both have their pluses. They both have their minuses. They're both good at predicting some things, and they're both bad at predicting other things. And so at the end of the day, they're both going to be useful to us here in organic chemistry. Certainly at the beginning of organic chemistry, in Organic Chemistry 1, we're going to use a lot of valence bond theory and talk about the hybridization of different atoms in a structure. We'll continue to talk about the hybridization of atoms pretty much throughout the entire time in Orgo 1 and Orgo 2. Later on in Orgo 2, we'll use valence bond theory, we will use a lot more molecular orbital theory to really talk about some of the properties of reactions and explain some of these properties and explain some of the stereochemical, especially stereochemical outcomes. We'll also use it to explain other things as well. And it's a really good handy tool to look at where electrons are in molecules. And so they're both, again, they both have their good things, they both have their bad things, but neither one of them is better than the other, in my opinion. And so what I want to do is I want to start off with valence bond theory, and then we'll move into molecular orbital theory, and then we'll then finish up with a discussion on intermolecular forces, and that'll be it for this video. So let me flip over to my screen and talk to you a little bit about this idea of valence bond theory, and we'll go from there. All right, so we're back here, and what I want to do is I want to start off with good old methane, CH4. And if I draw the Lewis structure, I know already that the geometry of this Lewis structure is tetrahedral. And this is tetrahedral. And we already know, and we have known, in other words, since before valence bond theory and molecular orbital theory were invented, we know that the structure of methane is tetrahedral. And so the question is this: if we take an X, Y, Z coordinate system, and we place on that coordinate system a carbon atom, what do we know about the electron configuration of a carbon? It's 1s2, 2s2, 2p2. This is the electron configuration for carbon. Well, let's just think about the 2s and the 2p orbitals. And so what we want to do is think about these orbitals. And so what if I have these valence orbitals for carbon and I draw them? Well, what do I have? I have a 2p orbital, and we know that that orbital is spherical. And what else do I have? I have some, that's a 2s orbital. And I have some p orbitals. We know that there are 3 of them. And if we remember from general chemistry, they line up on these different axes. So there's a pz, a py, and then a px orbital. And what do we know about these things, these orbitals, the shapes or the orientation of these orbitals? how is it that if I take a hydrogen that, of course, has a 1s1 electron configuration, an s orbital, and it interacts with an s orbital and three p orbitals, which are spherically symmetrical, or in the case of the p orbital, they're lined up perfectly along a xyz coordinate system, and therefore they're 90 degrees apart from each other. How do I get that then to become a shape of a tetrahedron? And if you remember, in the tetrahedron, the bond angles are 109.5 degrees. That ain't 90. And so what's going on here? And so this is where valence bond theory came in. And they said, well, we can use mathematics to take this s orbital and these three p orbitals, and we can mix them up in a way that then matches our experimental observations. So what we have then is we have the normal ground state electron configuration for a carbon atom. And then what we're going to do is we're going to imagine it undergoing an excitation where one of those electrons in the 2s orbital is promoted to a 2p orbital. So we still have 2s, we have 2p. So I've got one single electron here, one here, one here, one here. And then this is, and we're not going to do the math because this is organic chemistry, not physical chemistry. It's not calculus. It's not quantum mechanics. So we're going to leave the math to those guys. So what we're going to do is we're just going to, what I say in class is we're going to put it in a bag and we're going to shake it up. And the shaking is the mathematical mixing. And so what do we get at? We get 4 degenerate hybrid orbitals. So what did we do? We took 4 orbitals, we put them into the bag, we get 4 orbitals out. So any number of orbitals you put in, that's how many orbitals you're going to get out. This is just one of the facts, one of the properties of this particular mathematical mixing. Then also what we're going to do is we're going to say these are hybrid orbitals. If you remember that this is essentially an energy graph, and if I think about it in terms of an energy graph, then the p orbitals higher energy than the s orbitals. Then at that point, when I line everything up on an energy graph, these are degenerate. And that, remember, degenerate means of the same energy. But these are now hybrid orbitals. Why are they hybrids? Well, it's a hybrid between an s orbital and a p orbital. We put an s orbital and 3 p orbitals together and we mix them up. And now they all are exactly the same. They're all hybrid orbitals, and we're just going to give them a new name. They're sp3 orbitals. And so what we did is we mixed them together, and we lowered the overall energy a little bit. They're in between the p and the s, but they're overall lower in energy. And so now we can take these 4 unpaired electrons, populate them in these 4 degenerate sp3 orbitals, and we can then maybe mix them with 1, 2, 3, 4 electrons from a system of hydrogens. And those s orbitals on hydrogens overlap nicely with sp3 orbitals. Everything's going to become paired up, and then that's the where do we get this tetrahedral shape? Well, these hybrid orbitals line up perfectly in a tetrahedron according to valence bond theory. And so we can sort of do the same explanation. We can say, well, what happens with situations when you only mix maybe 3 of the orbitals? What about these 3 orbitals? And this is a situation when the hybrid orbitals are mixed with s and only 2 of the p orbitals. Well, you get a situation where you're going to get 1, 2, 3 degenerate sp2 orbitals. They're going to lower themselves in energy, but you still get 1 leftover unhybridized atomic p orbital. And this would be the situation when you have sort of like a double bond. If we redraw this double bond, and we redraw it from the perspective of it being sort of flat so that we can see there's the double bond, there's a hydrogen moving away from us and a hydrogen coming towards us. These orbitals are sp2 orbitals. and there's an unhybridized p orbital left on the carbon interacting with a unhybridized p orbital on, or a p orbital on the oxygen. The oxygen didn't hybridize, it's just the carbon. And so this is where we would get the electron configuration that involves sp2. And they get a similar situation going on with sp. You're only going to hybridize an s orbital and one p orbital. All right, so what's valence bond theory really good for? Valence bond theory is really good for producing pictures that look like bonds that we are familiar with, like atomic orbitals. But that's about as far as it goes from the picture's perspective. But the other part is that it ratchets up really well with Lewis structures. And so when we think about something like CH4, or we go back to our formaldehyde, this guy here, or maybe we think about something like acetylene that has a triple bond, what we get to immediately is that the different Lewis structures are really good at conveying to us instantly this idea of hybridization. And then we can talk about, especially when it comes to sp2 and unhybridized p orbitals, they're really going to be important, especially like in aromaticity. And so at the end of the day, what you should be able to do is look at a Lewis structure, whether it's a Lewis structure like this, or it's a line structure like this, and you should be able to take your pencil and point to any particular atom and then tell me what the hybridization is, whether it's sp2, whether it's sp3. Yep, see, I messed this one up already. Whether it's sp3, sp2, or possibly even sp hybridized. And the way to think about it is that this hybridization always is associated with the electron geometry. If the electron geometry is tetrahedral, it's sp3. If the electron geometry is trigonal, planar, the hybridization is always sp2. And then if it's linear, the hybridization is always sp. And so this is what you can do as an organic chemistry student to sort out the difference between the hybridization of the different atoms. And so another thing that I'll want to throw out at you is this idea of sigma bonds and pi bonds. But before we get to that, I need to go over molecular orbital theory. And so what I want to do is I want to switch gears now and kind of talk about two of my favorite things. One of these things is O2, and the other one is N2. And so if you look this up online, you'll find out that oxygen is actually magnetic and nitrogen is not. And the thing that you have to know is that you need unpaired electrons to have this magnetism. It's called paramagnetism. And so in order for you to be paramagnetic, you end up having to actually have unpaired electrons. And remember we said that Lewis structures and valence bond theory are very closely related to each other. And so if you think about the Lewis structure for nitrogen and the Lewis structure for oxygen, neither of them predict any sort of unpaired electrons. In fact, Lewis structures are really not good for predicting where unpaired electrons are. That's part of the limitation between valence bond theory and molecular orbital theory. So we know from experiment, because if you take liquid oxygen and you put it in a magnet, it sticks. So if you know that, then we got to figure out, well, okay, well, what's going on and how can we explain it? Well, what we can do is we can take atomic orbitals again, just like we did with valence bond theory, and we can put them in a bag and we can mix them up mathematically again, just like we did with valence bond theory. But instead of having a valence bond theory bag, we can have a molecular orbital theory bag where we do a linear combination of atomic orbitals. And once we do that, we end up getting this situation where and the other thing we're going to do is we're going to allow an orbital to be anywhere in the molecule. Another limitation of valence bond theory is that it really does restrict orbitals to be between two atoms only. And so once we do that, we get a different sort of picture. And so if we take oxygen, and again, of course, we're going to draw an energy diagram. And what I want to do is think about the electron configuration of oxygen. And I also want to then do the same thing and think about the electron configuration of nitrogen. So what is this electron configuration for oxygen? 1s2, 2s2, 2p3. If I did that right. Actually, it's 2p4. So I need to fix that real quick. Let me erase that 3. Come over here, put an sp4. Now, for nitrogen, our Lewis structure predicted this guy, and it's the nitrogen electron configuration 1s2, 2s2. This one is 2p3. And so what we're going to do is we're going to perform a linear combination of atomic orbitals. And what I want to do is I just want to make sure that we understand what I'm mixing here. I've got a 1s orbital and a 1s orbital. And what I'm going to do is I'm going to do this linear combination of atomic orbitals, and this is how this works. When we mix two orbitals together, we get two orbitals out. This is the same as it was before. Just like in valence bond theory, put two orbitals in, you get two orbitals out. There's a difference here. One of the orbitals gets higher and the other orbital gets lower. And so what we're going to call this is a sigma orbital, and then we'll call this a sigma anti-bonding orbital. So every time we combine two orbitals or sets of orbitals together, we get some bonding orbitals and some anti-bonding orbitals. Maybe we'll get some orbitals that are exactly the same energy where they started out, and we'll call those non-bonding orbitals. But that's for another consideration later. All right, so this is going to be true in both cases, right? I've still got 1s orbitals for each oxygen. They had been previously, I got a 1s here. It was fully occupied. I've got a 1s there. It was fully occupied. And now the same thing is going on here with the nitrogen, right? I've got a 1s orbital there, a 1s orbital there. I'm going to take my little molecular orbital theory mixing bag, mix them together. I get the same pattern that comes out. You don't have to know how or why this pattern is the way it is. It falls out of the mathematics. What you need to be able to do is draw them, right? And so now you've got two s orbitals. You mix them together. One comes high, one goes low. You get two orbitals out. One of them is a sigma orbital. One of them is a sigma anti-bonding orbital. And we put a little star there. And what we'll say is sigma star. All right, so then now that we've got that done so I got to add the electrons now. So I got still, just like before, I've got an electron here, an electron here, an electron there, an electron there. And so what I want to do is I want to keep moving up the electron configuration. And now I want to get to a 2s orbital. 2s orbital, I've got one there and one there. Well, how do these mix? Well, you already know the pattern. It's the same pattern as before. One goes up high, one goes low, two orbitals in, you get two orbitals out. And so I've got this orbital here, this orbital there. They both had electrons. And we'll come back and fill them in later. But like before, we get a sigma orbital and a sigma star orbital. And so what's going on here? It seems like this is an anti-bonding orbital, but it's lower energy than the bonding orbital right above it. Is that possible? Yeah, that's exactly what's going on. And so yes, that anti-bonding orbital is lower in energy. Okay, and so what we're going to do is we're going to do the same thing over here. 2s, we have an orbital, we have an orbital. I want to come in, I want to mix them. I want to mix them. I'm going to mix them. I want to draw the resulting orbitals. I get a sigma orbital and a sigma star orbital, and I have these electrons sorted out here. Okay, now here comes the p orbitals. So now I'm up to the 2p block, and I have 1, 2, 3 orbitals. I have 1, 2, 3 orbitals in my 2p block. All right, so this is just something, again, you don't have to know why this is the way it is. You can go to your physical chemistry class and look it up. If you want to learn out how to do linear combinations of atomic orbitals, you're going to need some linear algebra. You're going to need a little bit of calculus, and you're going to need a little bit more time. And so once you got your matrix algebra down, this is what we figure out. The pattern of combination looks like this. One, you get 3 orbitals that go up in energy. You get 3 orbitals that go down in energy. There are sets that are degenerate for both cases. You get sets that are degenerate for both cases, and their 2 degenerate sets are closest to each other, right? And so the two, remember, the degenerate sets are the ones that go up in energy, and the ones that go are the ones that are, excuse me, the ones that are the same in energy. All right, so for each atom you had S, P, or 2p4. So that means we have 1, 2, 3, 4 electrons in each one of those orbital sets. And so when we have nitrogen, we're going to do the same thing because, of course, it has the same exact electron configuration. You're going to end up with 1 that goes down. There are 3 that go down, 3 that come up. The degenerate orbitals are next to each other. And so I'll use these light blue lines to show you how they're all mixing together to do this. Okay. And then before, we, as before, we still have 1, 2, 3 only in this case. So we still have that electron configuration, but there's only 3. Okay, so now that we've drawn the molecular orbital energy diagram, where these orbitals in the middle are the molecular orbitals. These orbitals in the middle are the molecular orbitals. How did we make them? Well, we made them from linear combinations of atomic orbitals, and we made molecular orbitals with them. Okay, now that we've done that, let's populate electrons. And so we're going to take all of the electrons that are in the molecule and populate them exactly the same way as we would from bottom up, from lowest energy to highest energy, using the Pauli exclusion principle, using the Aufbau principle, and then filling them in until we run out. And so let's keep working. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 for nitrogen. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So molecular orbital theory matches up our prediction from valence bond theory. Do you see any unpaired electrons? I certainly don't. So it doesn't seem like there are. What about oxygen? I've got 14, 15, 16 electrons for oxygen. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So now all of a sudden, with those 2 extra electrons, I've got 2 unpaired electrons. Now, the orbitals that are here, singularly, non-degenerate, they're still sigma orbitals or sigma star orbitals. These degenerate orbitals are called pi orbitals. We get a pi anti-bonding orbital, and we get a pi bonding orbital. And we'll talk about in a second what that means as far as where the electron density is, because that's another thing that you're going to have to be able to get back or get from a Lewis structure or from a line structure, is not only the hybridization, but what kind of sigma and pi bonds are there. Of course, you're going to have to do geometry as well. So take a look at what our molecular orbital theory predicted for oxygen. It predicts that there are 2 unpaired electrons. So that prediction from molecular orbital theory matches up with our experiment. And so this is one thing that is good about molecular orbital theory. It predicts much better than valence bond theory, which can't do it at all, where unpaired electrons might be. But remember, in this case, these orbitals are allowed to be anywhere across the entire molecule. And so they don't really look like typical orbitals that you get involved with. They could look really funky. And so what I encourage you to do is look up some pictures of molecular orbitals, even for some basic molecules like benzene or something like that, and you'll see that they don't look like atomic orbitals at all. And so let's get to this last point before we move on to intermolecular forces. And this point is this idea of sigma and pi bonds. And so what we want to get at is kind of, we want to go back to valence bond theory and talk about what do we get when I have a doubly bound carbon. Let's say it was ethene. So this guy here, 2 carbons with a double bond in the middle of it, or in the rest of it, hydrogens. So what did we say about this situation here? We said that these carbons are sp2 hybridized. And if you remember, from the 3 p orbitals in the 1s orbital, we only took 2 of the p orbitals. So that means we've got 1 of the p orbitals that's yet unhybridized. And so what I do then is I say, okay, let's just draw the hybrid orbitals. So there's one of the hybrid orbitals. There's another one of the hybrid orbitals, and that's overlapping with a hydrogen. And the hydrogen is an s orbital. There's a hybrid orbital overlapping there, and a hybrid orbital overlapping here. It's overlapping with a hydrogen s orbital. That's what's causing this thing to be a bond. And then there is another hybrid orbital here. And these things overlap with each other, and that forms the bond in the middle. Okay, so what's a sigma bond? This is a bond whose bond density is along the internuclear axis. And so if I take my pen and I show you what I mean by the internuclear axis, here's one nucleus, here's another nucleus. If I draw an axis in between, that's the internuclear axis. If I do the same thing with hydrogen, that's the internuclear axis there, that's the internuclear axis there, that's there, that's there. And so what you find out is that those are all sigma bonds. And so let's take a look at our unhybridized p orbital. And what I'm going to do is I'm going to draw a really simplistic view of it, like this, unhybridized p orbitals. And what happens with the electron density here is that the electron density is shared like this. And now I'm using valence bond theory to talk about molecular orbitals, right? So I'm mixing them together, but it's easier to see. It makes more sense to see what this looks like. So this is above or below or essentially outside of the internuclear axis. And so now what we have is we have a pi bond. Pi bond is where the bond or the electron density is outside the internuclear axis. Fix my spelling up there. Okay, so when I look at a molecule that has a Lewis structure, how do I sort out how many pi bonds and how many sigma bonds there are? Well, remember, it's ultimately just with geometry, and it's just with the Lewis structure. If all I have are single bonds, then they're definitely sigma bonds. Okay? And so, but what's going on right here with the double bond in the middle? Well, what happened here with this picture here? One of the bonds in the middle is a sigma bond. It goes along the axis. So one of them is a sigma bond. But the other one was outside of the internuclear axis. So it's a pi bond. So every time you see a single bond, it's always a sigma bond. Whenever you see multiple bonds, that's when you start to add different pi bonds. And so with a double bond, one of them, as we see here, is a pi bond, and the other one is a sigma bond. So there's one of each. Well, let's take a look at another situation. What if we had something like C2H2? So we draw this guy, and we remember that it's sp hybridized. That means there's one s orbital and one p orbital that's making hybrid orbitals. So I've got a hybrid orbital. Let's use the purple again. It's here. It's an sp orbital. I got a hybrid orbital here. Again, it's an sp orbital. If I draw it just a little better, it'll line up just a little better. That was just my drawing. And then, of course, I've got yet another hybrid orbital. It comes out this way. Remember, it's linear. And now if I take some hydrogens and their s orbital and I overlap them, then I've got that situation there. Hopefully you can already see that these orbitals are all that I've shown you. These are all sigma bonds, or these bonds are all sigma bonds. Well, what's going on here? Well, if I think about an XYZ coordinate system, then I still have two unhybridized p orbitals, the ones that are going up and down just like I did before, and now the ones that are coming that are along the y-axis, so in and out of the page. And so I've got these two unhybridized p orbitals. They still have electron density going in them, but both of these are outside of the internuclear axis. So in this case, I still have pi bonds and sigma bonds. So what does that mean over here in this other molecule? Well, I still have any single bond. Those are sigma bonds. But what happens with this multiple bond? Well, just like before, one of them is sigma, but now I have two pi bonds. So how did it work out? Let me review this. If it's a single bond, it's a sigma bond. If it's a double bond, it's one sigma and one pi. That adds up to both of the bonds. So if it's a triple bond, then it's still one sigma, but now I have two pi bonds. And so your question's going to end up being something like this. When you have a molecule or a line structure, I'm going to show you something like this, and I'm going to say, how many sigma bonds and how many pi bonds are in the structure? Well, you're going to count up the double bonds and multiple bonds and say, one of these is sigma and one of them is pi. One of these is sigma and two of them are pi. And then all other single bonds are sigma. And so how many sigma bonds do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Don't forget to count the hydrogens that aren't shown, right? Hydrogen, 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 hydrogen. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How many pi bonds are there? Well, there's 3. And so that's going to be your job. All right, so here's the final bit that I want to get at for this particular lecture. Let's talk a little bit about intermolecular forces. We've been talking about Lewis structures at this point, and so what we want to get back to is Lewis structures, electronegativity, and the different types of intermolecular forces. Intermolecular forces are all about uneven distributions of electrons. That's it. In any case, it's all about the uneven distribution of electrons. I don't care if you're talking about a dispersion force. I don't care if you're talking about dipole-dipole forces. I don't care if you're talking about hydrogen bonding or even ionic forces. It's about uneven distributions of electrons. End of story. And so what do we have? Electrons are quantum mechanical particles. And if you think about a quantum mechanical particle, it has a probability factor. It doesn't live in a deterministic world. So what's the probability that an electron on a molecule in your shirt will be found at your neighbor's house? Well, you don't anymore go say it's impossible. You just say it's not likely, but there is a small probability. It's very small. And so what does that mean with a molecule? Even a molecule like H2, where the bond is completely nonpolar from your idea that hydrogens are exactly the same electronegativity, so we don't have to worry about whether or not the electrons are unevenly distributed. It's not polar. Well, it doesn't have a permanent dipole moment because the electrons aren't permanently unevenly distributed, but because they're probabilistic particles, then they can have a small probability to become unevenly distributed. And so that's what a dispersion force is. It's this instantaneous dipole moment formed from the probabilistic behavior of electrons. So what molecules can have dispersion forces? Well, any molecule with electrons. Well, what molecules have electrons? All of them. So every molecule has dispersion forces. What we're going to concern ourselves with in organic chemistry are primarily polar molecules and hydrogen bonding. What do you need to be polar? In order to be polar, you need a permanent molecular dipole moment. Looking at the two structures, not including the H2, the two molecules here have bonds that are technically polar, even though some folks are going to yell at you and say, oh, the electronegativity of hydrogen and carbon is roughly the same. Blah, blah, blah. It ain't exactly the same. It's not exactly the same, so it's going to be polar to some degree. So if we think about the molecule in 3 dimensions, and I want to redraw that molecule in 3 dimensions because I hadn't, the other one is, this one is not 3-dimensionally accurate. Remember, it's tetrahedral. And so now how do I deal with all the different bond dipoles? Carbon is slightly more electronegative than hydrogen. And so if I were to draw these individual dipole moments, the hydrogen has electron density pulled away from it by carbon. But what do these vector arrows show you? Even though they're small vector arrows, and for the most part, we would say that a carbon-hydrogen bond is nonpolar, I want to show it just for purposes of demonstration. This molecule is quite symmetrical. So that's why this molecule is nonpolar. All of these dipole moments, due to the symmetry of a tetrahedron, all cancel each other out. Well, what about CH2O over here? Well, oxygen is clearly more electronegative than carbon. So the electrons get pulled this way. Hydrogen more electronegative than carbon. It gets pulled that way. So you see that the arrows all point in the same general direction, and that's up as far as the screen is oriented. So there is a permanent dipole moment for formaldehyde, and so it points in that direction where the oxygen would be partially negatively charged, and this side of the molecule would be partially positively charged. And so this has a permanent dipole moment. It's a polar molecule. All right, what's this business with water? So if I take water and I show you the bent geometry of water, go ahead and add the tetrahedral structure that has the 2 lone pairs, we get the same sort of situation. This molecule was symmetrical. This molecule is not symmetrical. And this molecule is not symmetrical. Symmetry leads to nonpolarity. That's unsymmetric, non-symmetric molecules leads to polarity. This molecule is polar. When you've got a bond dipole that looks like this, a bond dipole that looks like this, and then of course, electron density is going to be moving towards the lone pair of electrons. Lone pair is more negative than the atom will ever be, right? So the lone pairs have more of a negative charge. And so there is this permanent dipole moment that moves this way in the molecule. The side of the molecule with the electrons is negative. The side of the molecule with the hydrogens is positive. And so that's just a fact of life. So water is also polar. But water has a very special type of bond. Remember that oxygen, fluorine, and nitrogen are very electronegative. they're so electronegative that these bonds, while they're all polar, they all have dipole moments that point this towards the electronegative atom. They're just particularly very polar. And because they're particularly very polar, we're going to give them their own special name of hydrogen, of interaction, intermolecular force, and we call it hydrogen bonding. Well, you're going to say to me, well, if it's just really a bit of polar, if it's just a special bit of polar interaction, why are we going to give it its own name? The reason why we give it its own name is because that it's strong enough that it provides its own trend in physical properties. If you take a look at the different boiling points for molecules, you see that something like C ethane is essentially a gas at room temperature. If I add a sulfur to it, sulfur is pretty electronegative. But then I can add, so its boiling point is much higher. Now, if I add an oxygen to it, even though oxygen is smaller and less polarizable than sulfur, it's got hydrogen bonding. So the boiling point of ethanol is much higher than ethane thiol. And so this is the end of the video. This is really where I wanted to go with intermolecular forces. So once you've identified the different types of intermolecular forces in order of strength, dispersion, polar forces, and hydrogen bonding, then you can sort of identify the differences in physical properties. So why does an alcohol have a higher boiling point than an alkane or an alkene? Because they got hydrogen bonding. That's the end of the story. That's really what it's all about. Or why does an alcohol have a bonding, or excuse me, a boiling point that's larger than an aldehyde or a ketone, even though they're both polar? Well, it's because the alcohol can do hydrogen bonding. And so that's going to come up a lot in organic chemistry. So that's the end of the video here. If you got some questions, you know how to get a hold of me.